Hi. Linear regression is a very simple technique that is widely used in statistics and machine learning to infer data. In this video, I will try to explain to you the idea and the theory behind it. Let us suppose we have data that represents some characteristics of a group of persons. Say, for instance, their heights and weights. And suppose for one of those persons, we have a piece of data is missing. Like, for instance, for this particular person, we don't know her or his weight, but we know her or his corresponding height. So the question is, can we infer the weight of this person by knowing her or his height, plus a set of heights and weights of data for similar persons? First of all, we need to plot these observations into some scatter plot like what you are seeing here. Here we can see some sort of correlation between heights and weights. What does it mean is that as height is increasing, the corresponding weight is also increasing, and the other way around. As height is decreasing, as you can see here, the weight is also decreasing. Actually, correlation between both height and weight is a very important characteristic in order to apply linear regression. Otherwise, we cannot apply it. So if this condition of correlation between both height and weight is valid, then we can go through the linear regression. So after making sure that we have certain level of correlation between both height and weight, then we can represent the relationship between both of these variables as a line like this. In such case, we can define one variable, say the weight of one observation, which represents one person, by knowing only his or her height. So as a reminder for you, we know that the linear equation is represented by this very simple mathematical formula, y equal mx plus b, where m represents the slope of this linear function, and b represents the point at which y intersects, the linear function intersects with y-axis at x equals 0. So the question now, if we have already a correlation between both x and y, or between both height and weight, and we need to define such linear function, the question will be, which line should we choose to represent the relationship between x and y? As you can imagine, we have infinite number of lines that can represent the relationship between height and weight, or between x and y. So the question is, which line should best represent the relationship between both variables? This is the idea behind the linear regression. And now we'll jump to the theory of it, which represents how we can select such line. Actually, people have agreed that a very convenient way to select a line that represents this correlation or this relationship between x and y is that we can say the best fit or the best line could be the line which minimizes the distances between the true observations here and the line itself. So we need to select a line such that when we sum up all of the distances between this line and all of the true observations, we have the summation is as minimum as possible. Actually, this technique is called the least square approach, and it is represented by this function, E of w equal 1 over n multiplied by the summation of the differences between the true observations, represented by y super I, and the linear function itself, represented by f of x over I and w, where x of I represents the variable x, and w represents a vector of coefficients. For instance, in our case, it represents both the slope and y-intercept coefficients. So actually E of w has multiple names that you can find in literature. Sometimes it's called error function or objective function, some other times it's called cost function. So it has a very large list of names, but it has always the same idea behind it. And in our case, we used this particular formula for error function, which is called the mean square error, or MSE. It's a very simple to understand. It's called the mean square simply because it squares the summations, or sorry, square the differences between true values and the linear function, and it computes the square value to overcome the differences of whether the difference will become positive like this line or negative like this line. So we need to put all of the values regardless of its sign, such that we can have good estimate of the error. And after summing up all of the differences, we compute the average of them by dividing them by n, which represent here the number of observations. And we do this average step in order to make sure that we can compare our error function using different subsets of data, or subsets with different sizes of data. So now let's put it more formally or more mathematically. We have this least square approach, and we want to minimize this error function here. We knew now that y super I represents the true values, and f of x super I and w represents the line itself that we try to find. And the goal is to find the list of coefficients that can minimize this error function. So the f of x super I and w is called the linear regression function, or sometimes it's called the hypothesis function, and it is very simply defined as any linear function. It's defined by the w0 plus w1 multiplied by x of I, where w0 in our case is the y-intercept at x equals 0, and w1 represents the line slope. So now, as we understand the goal behind the linear regression, or the theory behind linear regression, which is minimizing an error function, which we have explained before, now we will try to apply this technique or the theory. As a reminder for you, I just wanted to show you how we minimize or maximize a given function. Let's suppose we have this green function here, f of x, and we try to find the global minimum or global maximum of it. Here, as you can see, this is the point A corresponds to the global maximum of f of x, and point B corresponds to the global minimum of f of x. And the idea here, in order to find either the maximum or the minimum value of f of x, we learned in calculus that firstly we need to calculate the derivative f dash of x of this function, which is here represented by the blue curve here, and we equalize the f dash of x, or the derivative of x, to 0 in order to solve for the coefficients of this function of f of x. And once we solve the group of or the system of equations when we equalize it to 0, then we can find the global minimum or the global maximum of the original function. So officially the procedure is to compute the derivative of f of x, so f dash of x in our case, for each coefficients w in the vector of coefficients, and secondly to set f dash of x equal to 0, and after obtaining the system of equations of f dash of x equal to 0, then we solve this set of equations to obtain the values of coefficients such that we obtain our required linear function. So let's put it that way. We need to find the vector of coefficients, which in our case has only two coefficients, w0 and w1, such that we need to minimize this function. So let's firstly compute the first coefficient w0, which represents the linear intersect with axis y at x equals 0. So we compute the derivative of e of w. Here we have 1 over n with a sigma of this expression. We try to differentiate this value with respect to w0. So first of all, we want to resolve this square bracket. So here we will have y super I square minus 2 multiplied by y super I multiplied by this small component plus w0 plus w1 x super I all to the square. So we will simplify it once again. So here we have this term as it is, y super I square minus 2 multiplied by y super I multiplied by w0 minus 2 w1 x super I y super I plus and then we will resolve this part which will become w0 square plus 2 w0 w1 x super I plus w1 square x super I square. Again, we will try to simplify the expression, or rather we will try to start computing the derivative now. So when we differentiate this expression with regard to w0, we will have this term will be deleted, this term will be minus 2 y super I, this term will be deleted, this term will be plus 2 w0, and this term will be 2 w1 x super I, and this term will be deleted, and we end up with this expression. Again, we will try to simplify it by sending the 2 outside the sigma signal. So we'll have it now expressed as minus 2 over n multiplied by the summation of wi minus the w0 plus w1 x super I. And this is the simplest formula of the derivative of the error function with respect to the w0 coefficient. Secondly, we will try to compute the derivative of the error function with respect to the slope w1. We have the same expression here, but now we will differentiate with respect to w1. Very simply, we will have this term will be deleted, this term will be deleted. Here, this term will be minus 2 x super I, y super I. This term will be deleted, this term will be plus 2 w0 x super I, and the last term will be plus 2 w1 x super I square. Again, we have a simpler formula for the derivative, and we will send the 2 outside the sigma signal again, and we will have again this simpler formula for the derivative. So now, after obtaining both values of derivatives, we need to equalize them to 0 and try to solve the corresponding system of equations. So we will put both expressions, minus 2 over n sigma of y super I minus w0 plus w1 x super I equal to 0, as well as the other equation corresponding to the x1. And now we have two equations in two variables, so it is doable mathematically. And we have very two common approaches to solve this system of equations. The first one is called the closed form approach, and the second method called the gradient descent algorithm. And in the next video I'll try to explain both approaches in more detail and show you how we can solve the problem of linear regression using these two approaches. Thank you.